Everyone has heard of Bitcoin. Millions buy, sell, and trade it every day, treating it as a digital currency outside the traditional banking system. Yet, if you ask someone to physically describe what a Bitcoin actually is, or what computers are doing when a transaction happens, you usually get a blank stare. To understand exactly what this technology is, we need to completely drop the vague analogies to gold mining. We are going to build a cryptocurrency from scratch. Let's look at this diagram showing a basic digital ledger. Imagine you and your friends exchange money frequently for things like dinner or rent. Instead of trading physical cash every time, you set up a communal website where anyone can log debts. You add a line that says, "Alice pays Bob $20, keep a running tally, and agree to settle up the actual cash at the end of the month." The problem with a public website is that anyone can add a new line. Bob could easily type out, "Alice pays Bob $100" without her approval. In a system like this, there is no built-in way to verify that a transaction is what the sender actually intended. When you use a credit card or an app to send money, a central bank sits in the middle of the transaction. They act as the sole authority, verifying your identity and ensuring nobody spends money they don't have. If we want to remove that bank entirely, we have to find a way to trust the data itself. We need a system that perfectly secures our list of transactions and blocks any forgery entirely on its own. We can solve the forgery problem using a tool from cryptography called digital signatures. To use them, every person generates two strings of data: a private key, which you keep entirely secret, and a public key, which you share with the world. You use your secret private key to sign your outgoing payments, and everyone else uses your public key to verify that the signature actually came from you. Let's look at this diagram showing how the math works. When Alice wants to send $20, a computer function takes her exact message, combines it with her private key, and outputs a massive string of 256 bits. This string of ones and zeros is her digital signature. Because the signature is intrinsically tied to the exact text of the message, Bob cannot change the amount owed. If he tries to alter even a single number in the transaction, the resulting signature completely scrambles into an entirely different sequence, making the forgery instantly obvious to anyone checking his math. With signatures securing our identities, we add one simple rule to stop people from racking up debt. You can only spend money that someone else has already sent to you on this specific ledger. Once identities are mathematically locked and balances are strictly enforced by the system, you never actually need to cash out. The list of transactions stops being a way to track US dollars and becomes its own independent thing. The history of the ledger is the currency. We still have a problem. If this secured list lives on a single website, we still have to trust whoever owns the servers. To remove that central point of failure, we distribute the list to thousands of individual computers. Everyone keeps their own private copy of the ledger. But this creates a massive synchronization issue. When Alice broadcasts her payment to the network, we have to guarantee that every single person updates their private copy with the exact same transactions in the exact same order. If network delays cause messages to arrive at different times, or if a malicious user broadcasts conflicting payments to different people simultaneously, the network fractures. Half the computers think Alice has the money, and the other half think Bob has it. For a digital currency to survive, it requires a mechanism that forces thousands of completely anonymous strangers to mathematically agree on one single definitive timeline of events. The solution relies on a specific mathematical tool called the SHA-256 cryptographic hash function. This chart shows how SHA-256 operates. It can take any size block of data, process it, and output a completely unpredictable string of exactly 256 bits. This function is a one-way street. You can easily calculate the output if you have the input, but no computer on Earth can look at the output and reverse engineer the original data. To force the network to agree on a timeline, we bundle pending transactions into a single block and require users to play a mathematical guessing game. They must rapidly attach random numbers to the block and run it through the hash function over and over until someone gets lucky enough to find a hash that starts with 30 zeros. Because guessing and checking is the only way to find this specific number of computational energy, it acts as a permanent, unforgettable seal on that specific block of transactions.
We then require that every new block must contain the hash of the block that came before it. If a hacker tries to alter a transaction from the past, it changes that block's hash, which instantly breaks the sequence of every single block that comes after it. To maintain the lie, the hacker would have to redo the massive computational work for the altered block and every subsequent block. This leads to the golden rule of decentralized consensus. The network is programmed to always trust the longest chain of blocks. Because producing a valid chain requires physical computing power, it becomes mathematically impossible for a single malicious user to outpace the combined computational work of the rest of the network. The people racing to solve these hash puzzles are called miners. As an incentive for dedicating all that computer power, the network rewards whichever miner successfully seals a block with newly generated currency. This block reward is the only way new money enters the economy, and it will systematically decrease until a hard cap of 21 million is reached. This precise architecture of digital signatures, cryptographic hashes, and mathematically linked blocks is the actual Bitcoin protocol running globally right now. You don't need to know how to calculate a 256-bit hash to send a digital payment, just like you don't need to know the engineering of a credit card reader. But understanding the specific machinery underneath strips away the vague analogies of gold mining and reveals exactly what your money is doing. Bitcoin is a brilliantly engineered, perfectly decentralized ledger. The mathematics secure the network, the miners process the data, and that long, mathematically locked history